Good morning, everyone. In today's video, we'll go through the numericals. Okay, that we have seen the theory in the previous class. A three-phase, four-pole, 50 Hz induction motor has 24 stator slots and 28 rotor slots. Prove that it has a tendency to run as a synchronous motor at 214.3 RPM. Okay, so this numerical is somewhat similar to the theory, right? So since we have not covered much of the theory on this, I thought would be a different type covering it through the numerical. So solution, synchronous speed ns is equal to 2 into f by p, so 2 into 50 by 4, which is 25 rps. The order of forward rotating field produced by stator slotting n is 2 into ss by p plus or minus 1, where this ss is the stator slots and p is the number of poles. So 2 into 24 by 4 plus 1, which is 13. It revolves at a speed ns, okay, by 13, okay, that is the n by 13 with respect to the stator. The order of backward rotating field produced by the rotor slotting n dash is 2 into SR by P plus or minus 1, where this SR is the rotor slots and P is the number of poles. Okay, so here it is 2 into 28 by 4 minus 1, so which is 13. The speed with respect to rotor is minus ns minus nr by 13. So these are the standards. Okay, the speed with the rotor the speed with respect to rotor is minus ns minus nr by 13. The rotor revolves forward at a speed nr, and therefore it revolves its 13th harmonic at a speed of minus ns minus nr by 13 plus nr, okay, with respect to stator. Hence, in order that the two fields may revolve synchronously with respect to each other, okay, so hence in order that the two fields may revolve synchronously with respect to each other, ns by 13, okay, so that is what we have here, okay, ns by 13, and then nr minus ns minus nr by 13. Okay, so on solving that, we get nr is equal to ns by 7, so it is 25 by 7, right, so 214.3 rpm, 25 by 7 rps, and which is equal to 214.3 rpm, right? So the motor has the tendency to crawl at 214.3 rpm, okay, which is fixed due to the harmonic synchronous torque. Okay, so this is what we are. So conversion from this to this is by multiplying it by 60. Then the next is, for the same above, calculate the order of slot harmonic produced. Find the angle through which the bar must be skewed to eliminate them. Find the effect of skewing on the lower order harmonic. Okay, so the same that the data we have, that three phase, okay, 4-pole 50 Hz, right, induction motor with 24 stator slots and 28 rotor slots. The order of the slot harmonic n is equal to 2 into ss by p plus or minus 1. Okay, so the stator slots as well as p is the number of poles. Okay, so for that we get 13 and 11. So 11th is the higher order and 11 is the low order. So it says to eliminate the high order, so that you have to eliminate the 13th harmonic, right? So angle of skew, right? So we know the skew is that the rotor bar which are at an angle. Okay, so theta s is equal to 720 into n into p. Okay, so 720 by 13, that is the harmonic, into number of pole, which is 4. Okay, we get it 13.85 mechanical. Okay, so this 13.85 degrees mechanical. So electrical angle of skew, okay, theta sk is equal to p by 2 into theta mech. Okay, so we get 4 by 2 into 13.85. okay, so which is 27.69 degree, or in radians it is 0.4834 radians. So distribution factor for 11th harmonic, right, that is KDN or KWN that we have, which is given by sine n theta sk by 2 divided by n theta sk by 2. Okay, so sine of 11 into 0.4832 by 2 divided by 11 into 0.4832 by 2, right, so which comes up to 0.1754. okay, so therefore the 11th harmonic EMF with skewing is reduced to 17.6% of the value obtained without skewing. Okay, so almost reduction by 82%, right, so it is therefore 11th harmonic EMF with skewing is reduced to 17.6% of the value without skewing. Okay, the next problem, 11 kilowatt 3 phase 6 pole 50 hertz 220 volt star connected induction motor has 54 stator slots, each containing 9 conductors. Calculate the values of bar and end ring currents. The number of rotor bar is 64. The machine has an efficiency of 0.86 and a power factor of 0.85. The rotor MMF may be assumed as 85% of stator MMF. Also find the bar and the end rings sections if the current density is 5 ampere per millimeter square. Solution, stator current per phase, okay, it is 11 kilowatts, so 11 into 1000 divided by root 3 into voltage 220 into 0.86 the efficiency and 0.85 the power factor, which will give us 39.49 ampere approximated to 40 ampere. Number of stator conductors, right, so it is 54 into 9. Okay, it is given, right, 54 into 9, which is 486 stator conductors. So stator term per phase, okay, is TS, which is 486 by 6, 3 into 2, okay, which is 81. Stator MMF, right, which is equal to 3 into ISTS, so 3 into 40 into 81, which is 9720 ampere. So rotor MMF is said to be 85%, so 0.85 into 9720, which is 8262 ampere. Rotor MMF is also equal to SR into IB by 2. Okay, so the basic equations that we have, so it is 64 into IB divided by 2, so which is 32 IB. Therefore these two represent the same rotor MMF, so 8262 is equal to 32 IB. Okay, so therefore IB is equal to 258.18 ampere approximated to 258 ampere. So end ring current IE is equal to SR into IB by pi into P, that is the number of poles. So SR is 64 into 258, which is calculated, divided by pi into 6, that is the number of poles. So which is 875.98 amperes approximated to 876 amperes. So now area of each bar AB will be IB by 5. Okay, so this is IB by 5 because it is 5 ampere per mm square the delta, that is the current density, so which comes to be 51.6 millimeter square, and the area of each end ring, that is AE, is IE by 5. So IE is 876, that is 875.98 approximated to 876 divided by 5, which is equal to 175.2 millimeter square. The next numerical, a 3-phase 2-pole 50 Hz squirrel cage induction motor has a rotor diameter of 0.20 m and a core length of 0.12 meter. The peak density of air gap is 0.55 Weber per meter square. The rotor has 33 bars, each of resistance 125 micro ohm and a leakage inductance of 2 micro Henry. The slip is 60%. Calculate first one, the peak current in each bar. Second one is I square R loss. Third one, rotor output. And last one, that is the torque exerted. Neglect the resistance of end rings. Okay. So solution, synchronous speed ns is equal to 2f by t, which is 2 into 50 divided by 2, which is 50 rps. Actual speed of rotor nr is equal to 1 minus s into ns. So the s is a slip which is given as 6%. So 1 minus 0.06 into 50, which is 47 rps. So peripheral speed of the stator field, right, which is given by pi d ns, okay, is pi into d 0.2 meter into 50, that is 31.42 meter per second. On similar basis, peripheral speed of the rotor will be pi d nr, so it is pi into 0.2, that is a d into 47, which is the nr, which is equal to 29.53 meter per second. Next, so the relative speed of rotor bars with respect to stator field, that is V, which is 31.42 minus 29.53, that is the speed of the rotor as peripheral speed of the rotor and the peripheral speed of the stator field, okay, the difference of that, which is 1.89 meter per second. So maximum EMF in each bar will be Bm L into V. So 0.55 the maximum flux density into 0.12 the length and 1.89, that is the V, the relative speed. So it is 0.125 volt. Therefore slip frequency we know S into F, so 0.06 into 50, which is 3 Hertz. So reactance of each bar is equal to 2 pi FL. So 2 pi into F, which is 3 into 2. So it is equal to 37.7 micro ohm. So impedance of each bar will be square root of R square plus XL square. Okay, so R is 125 micro ohm and 37.7 is the resistance, reactance. So it will, we get the answer impedance to be 130.6 micro ohm. So maximum current in each bar will be 0.125 divided by 130.6 into 10 raised to minus 6. It is nothing but I is equal to V by R. So, or here it is the Z, V by Z, so which is equal to 957.1 ampere. So the RMS value of the current IB is 957.1 by root 2. So maximum and the RMS values of the bar current. So rotor I square R losses, okay, so which is equal to SR IB square RB, so which is equal to 33 into 676.8 square into 125 micro ohm, so which used to be 1890 watt. So output is equal to rotor I square R loss into 1 minus S by S. Okay, so that we get by this relation, very known relation, rotor copper loss to rotor output is equal to S by 1 minus S. So from that output will be, right, So copper loss into 1 minus S by S, that is what is being here. So it is 1890 into 1 minus 0.06 divided by 0.06, which is 29.61 kilowatt. Therefore the torque is given by 29.61 into 10 raised to 3 divided by 2 pi into 47, right? So which comes around 100.3 Newton meter, right? So for this the equation is from this: output is equal to omega T, right? So T will be Pm by omega 2 pi F. Output that we have got 29.61, okay, divided by 2 pi F. So it is 100.3 Newton meter. Next problem, a 15 kilowatt 3-phase 6-pole 50 Hz squirrel cage induction motor has following data: stator bore diameter 0.32 meter, number of stator slots 54, axial length of the stator core 0.125 meter, full load power factor 0.85, number of conductors per stator slot is equal to 24, current in each stator stator conductor is 17.5 ampere. Design a suitable cage rotor giving the number of rotor slots, section of each bar and section of each ring. Full load speed is to be at least 950 rpm approximately, right? Use copper for rotor bars and end rings. So the resistivity of copper, which is also given, is 0.02 ohm per meter per millimeter square. So solution: the number of rotor slot is assumed a pair of poles greater than the number of stator slots. Okay, so this is we have seen in the derivation in the principles. Okay, so why it should not be same or why it should be more or less. The number of rotor slots SR is equal to SS plus P by 2. Okay, so 54 plus 6 by 2, which is 57. So stator slots are 54 and rotor slots are 57. So stator term per phase, okay, so 54 into 24 by 6. Okay, so that is the given data. Okay, so slots is 54 and stator conductor per slot is 24. Okay, so and divided by 6, so we are getting it as 216. So rotor bar current IB will be equal to 0.85 into 6 ISTS by SR. Okay, so since the power factor given right is 0.85, right, so on that basis also it is taken, and also we have the standard equation. Okay, so 0.85 into 6 into 17.5 into 216 divided by 57, which is 340 ampere. So taking current density of 7 ampere per millimeter square, area of each bar AB will be 340 by 7. Okay, so that is 49 millimeter square. So that is the area of the bars. Okay, then allowing 45 mm for projection of bar beyond core and skewing. Okay, so length of each bar, right, so with giving with some extra space. Okay, so for particular reasons like beyond core and skewing, length of each bar, that is what the earlier we had was 0.125, with addition of that for extra clearance, that is 0.045. okay, we get it to be 0.17 meter. Right. Next, copper losses in bar, okay, which is SR into IB square, right, into R is rho L by A, that is what is done, right. So 57 into 340 square into 0.02, that is the resistivity, into LB, that is 0.17, divided by AB 49. Okay, so with all those, so the copper loss in bar is 457 watt, right. Next, the current in each end ring IE is equal to SR into IB by pi P. So 57 into 340 divided by pi into 6. So it is 1030 ampere. Okay, so P is the number of poles, and this equation also we have from the standard derivation. So taking current density of 7 ampere per millimeter square for end rings, area of end ring AE is equal to 1030 divided by 7, so which is 147 millimeter square. Okay, so taking the ring section as 15 mm deep and 10 mm thick, that is the DE and the TE. So the area of the end ring AE is equal to DE into TE. Okay, so which is 15 into 10, so it is 150 millimeter square. The next is mean diameter of the ring. Okay, so already it is given as 0.32. Okay, so this is actually the what we have for the bore diameter, right? So we'll take a lesser diameter for the ring. So we have 0.32 minus 0.015, right? So which comes up to be 0.305 meter. Okay, so copper loss in end rings is 2 IE square, right, rho pi dr by AE. So the length is pi into d, right? So that is the length, okay, the circumference. So it is 2 into IE square, okay, so which is 1030 square into 0.02 the resistivity into pi into dr, that is what we have here, 0.305, okay, whole divided by AE 150 mm square, that is this what we have. So from that the copper loss in end rings that we get is equal to 271.07 watt. Okay, 271.07 watt. So the total copper loss is equal to 457 plus 271, that is in the end rings and in the bar, so which is equal to 728 watt. Okay, so again from the basic equation, S by 1 by S 1 minus S by 1 minus S is equal to rotor copper loss divided by rated output. So copper loss is 728 and 15 kilowatt, so 15,000. So S by 1 minus S is 0.0485. okay, so on solving this we get S to be 0.0462, that is a full load slip. Okay, so which is 4.6%. So synchronous speed is 120 F by P, so 120 into 50 by 6000 RPM. The rotor speed is 1 minus S into NS, so 1 minus S, that is 0.0462 into 1000, which is 953.8 RPM, that is the rotor speed. Okay, stator speed being 1000, right, the synchronous speed being 1000 RPM and the rotor speed is 953.8 RPM. Therefore this speed of 953.8 RPM is nearly equal to the specified speed of 950 RPM. Going to the last numerical, a 90 kilowatt 500 volt 50 hertz 3-phase 8-pole induction motor has a star connected stator winding accommodated in 63 slots with 6 conductors per slot. If the slip ring voltage on open circuit is about 400 volt, find a suitable rotor winding stating number of slots, number of conductors per slot, coil span, slip ring voltage on standstill condition, and approximate full load current per phase in rotor. Okay, so assume efficiency of 90% and power factor of 0.86. So solution: stator turns per phase is equal to TS, which is 63 into 6 by 6, so 63. So stator voltage per phase is equal to 500 divided by root 3, so 289 volt. So taking 3 slots per pole per phase. Okay, so number of rotor slots SR will be 3 into 3 into 8. Okay, so it is 72. Okay, so 3 slots per pole is 3 and per phase is 3. Okay, so and the poles which is 8. Okay, so it is 3 into 3 into 8, which is equal to 7. Using star connection for rotor voltage at standstill, right? So which is 400 by root 3, 231 volt. Assuming kWs and kWr to be same, okay, that is the winding factor or distribution factor for stator and rotor to be same. So the turns, that is TR for the rotor, is kWs by kWr into ER by ES into TS, which is equal to 231. So this will be 1. So ER is 231 divided by 289 into TS, which is 63. Okay, so it is equal to 50.4 approximated to 50. So rotor conductors per slot is equal to 6 into 50 divided by 72. Okay, so approximated to 4, right? So we get more than 4 point something, so it's approximated to 4. So actual number of rotor conductors now will be 4 into 72, so that is, it is 288. So actual number of rotors turn per phase, so TR will be 288 by 6, which is 48. Okay, so earlier it was 50, so with the changes it is 48. So actual rotor voltage per phase at a standstill ER is equal to 48 by 63. Okay, so the TR and TS, okay, this is TR by TS into 289, which is the ES, so which is 220 volt. So that is the ER. Voltage between slip rings and standstill is equal to root 3 into 220, which is 381 volt. Okay. So coil span is equal to slots per pole, which is 72 by 8. So it is 9 slots. Coil span is 9 slots. So stator current per phase IS, which is 90 into 10 raised to 3, that is a 90 kilowatt, divided by root 3 into voltage into efficiency of 0.9 and power factor of 0.86. Okay, so which is 134.3 ampere. Since the power factor is 0.86, the rotor MMF may be taken as 0.86 times of stator MMF. So rotor current per phase IR will be 0.86 ISTS by TR. Okay, so IR, that is the rotor current, will be 0.86 into 134.3 into 63 divided by 48, so which is equal to 151.6 ampere. Okay, thank you. So for this video, in the next video we'll see the theory for the no load current as well as the numericals on the no load current. Thank you.